absolutely delighted to be in Australia in spirit, if not in person. I visited Australia and New Zealand recently, 3 times total, and I would really love to go back in person, but it just happens that this is my second talk in Australia this year in spirit, and well, that's certainly better than nothing. Okay, so I will talk about noisy billiards. And I'm going to start sort of in the middle of a story. So I will describe a certain model, and there's a reason why I'm interested in this model. But if I tell you the reason why I'm interested in this model, then this will take half of my allotted time. So I will start in the middle, and if I have time, then I will go back to the motivation. Probably I will not have time, but who knows. So the model is the model of billiard balls. So what you see on the left is a configuration of billiard balls that is very tight. Actually, there's a theorem that this is the densest packing of disks in the plane. And imagine that these balls, these billiard balls, are so close that it is impossible to trace their trajectories realistically on the computer. So that they are, the distances are so small. So what can we do? Can we simulate that? Well, one option is to simply give up trying to simulate trajectories and say that the balls collide randomly. So instead of trying to determine which pair of balls will collide next, I'm going to choose a pair of balls uniformly and say, well, they collide. So for example, I can choose this pair of balls and say, well, they collide. And then their velocities will change. But I want to also show another pair of balls. This. If I choose this pair of balls, then, well, I can tell them to collide, but their velocities will not change because their velocities point away from each other. So these balls, if they could, they would just fly away from each other. So the process will continue. I'm going to, quote unquote, do collisions randomly. I will choose pairs. And then after some time, I will get configuration of velocities that looks like the picture on the right. Please note that if I choose any pair of balls here, for example, these 2 balls, and try to collide them, right? I tell them to collide, they will not, because their velocities take them apart. And therefore, there will be no collision and no change in the velocity. And in this paper, Athreya with Athreya and Mauricio Duarte, they have a proof that this process stops. So for any configuration of, we call them pinned balls, any initial velocities, after a finite number of collisions, the system will reach the stable state. There are no more collisions. No 2 touching balls can collide because their velocities are such that, well, they will not change during the collision. There will be no collision. Okay. Well, maybe just say a word why I would even want to look at pictures like this. It turns out that when you study the number of collisions, there are good reasons to think that a great number of collisions will occur when the configuration is really tight. So that's a very sort of hand-waving, justification for this model. Now let's have a look at a different picture. So I'm not sure whether you can see this on your screen because it depends on the resolution and so on. But you see on the left, it is the initial configuration of velocities. So I even did not try to draw the balls. You cannot see the balls. What you can see is their velocities. They are, tiny vectors. And it is white noise in the sense that, well, this is how I generated these vectors. There are IID and two-dimensional normal, standard normal. And then on the right, you see the terminal configuration. So no more collisions are possible. So let me point out, first of all, that in the center, the collisions, not the collisions, the velocities, the terminal velocities appear to be small. And when we go to the boundary, the velocities seem to be directed in one way, sort of away from the center. Okay, so this is one particular simulation. But today, I'm really, I want to discuss a somewhat different simulation. Or, well, I've done a number of simulations of this type. The first thing I'm going to do is I'm going to apologize for the picture on the left. I'm sure you see those beautiful waves here. Actually, they are irrelevant because this has something to do with how I drew this picture, and they are meaningless. So please ignore this. I'm going to tell you what is actually meaningful here or important. All arrows on the left point to the left or to the right. They are all horizontal. This is the initial configuration. But they do not have the same length. Some of them are long, some of them are short. And the way I arranged for their lengths is that it's in, you know, there are lengths. Actually, not, I shouldn't say length because the length is always positive. The velocities or the speeds, right? The speed can be positive or negative. They form a sinusoidal function. So there's a sort of sinusoidal function here, like that. And the point is that, you know, some velocities are pointing to the left and they are about 0, then pointing to the right, then 0, then to the left, 0, and so on. Now, what you see on the right is a configuration in the middle of the simulation. So there are some regions where velocities are perfectly ordered, or at least they appear to be ordered, and they are pointing to the left. And there are some other regions where you have something like white noise, or at least some kind of chaotic arrangement of velocities. And well, a hand-waving explanation for that is that in some regions, velocities were pointing away from each other and the balls did not collide. But in some other regions, velocities, the initial velocities, were pointing against each other. So the balls collided. And since they collided, their velocity changed, and you know, there were lots of collisions in different directions, and they created this noise. Okay. So the picture on the left is the same one that you have just seen on the previous slide, and the picture on the right. The picture on the right is the terminal configuration of velocities. So once again, it is ordered in the sense that small velocities are in the center and large speeds are on the boundary, and they are more or less aligned locally. So these kinds of simulations were the starting point for my current project with Jeremy Hoskins and Stefan Steinerberger. And we were, you know, discussing what can be done mathematically about that. And Stefan was saying, look, we should work on the one-dimensional model because two-dimensional models are very hard. And I was telling Stefan, no, you're wrong. You see, the one-dimensional model is trivial. And for this reason, it's uninteresting. You see, in the one-dimensional case, the one-dimensional case is very special, namely energy packets are conserved. So you see, look at the two balls in the top row. It doesn't matter whether they are moving or not moving, whether they are, when they collide, they will exchange the velocity vectors. So what it means is that if you have some initial configuration of velocities, the only thing that happens on the in the one-dimensional case is that these velocities will be rearranged. So at the end, in the terminal configuration will be simply a monotone increasing configuration of the initial velocities. So what it means is that the whole evolution is some kind of sequence of random permutations. And of course, random permutations are interesting. I mean, so it's a field of study, but this has nothing to do with the two-dimensional case, because in the two-dimensional case, energy packets are not conserved. You see, what happens is that if you look at this component of the vector, it gets transferred to the other ball, but this component, the horizontal component, will stay with the same ball, which means that if you look at the four red vectors, they are all different, and there is no conservation of energy. So in two dimensions, there's redistribution of energy. So this makes considerably, this creates a considerably different model than the one-dimensional case. So here's what we are doing right now. It's a toy model, a one-dimensional model that tries to sort of mimic that two-dimensional model. So what we need is some kind of mechanism for energy redistribution in one dimension. And what we do is, well, something that is unrealistic in one dimension. But, well, as I said, it's a toy model. So what we do is we are going to collide 3 balls at a time, not 2 balls. And let V1, V2, V3 be pre-collision velocities. You should think about them as given numbers. And then V1, V2, V3 with tildes are post-collision velocities. Well, we are trying to determine what they are. Now, I don't want this model to be totally unrealistic. I want this model to retain some properties of physics models. So we construct the model in such a way that we have conservation of momentum and conservation of energy. So conservation of energy means that, well, first of all, these numbers on the left are given. So this is a constant. And what we have is we have 3 unknowns on the right. And then once again, what you have on the left is given, right? It's pre-collision. And you have 3 unknowns on the right. And these equations, well, these are equations for a plane and for a sphere. So the intersection is a circle, right? A circle in 3 dimensions. And what we do in our model, we choose the 3 velocities, V1, V2, V3, randomly, and more precisely uniformly on the circle. So this is the redistribution of energy, and please note that it is done in such a way that both momentum and energy are conserved. And then, so this is the redistribution of energy, but then we need collisions, right? That was the original model. So we choose 2 of these velocities. We'll say these 2, or rather we choose 2 balls randomly, either the pair on the left or the pair on the right, and we do the collision. Well, actually on the right, nothing will happen because these velocities are already ordered. The green velocity is positive, the red velocity is negative. So in this case, they're we're not going to rearrange them, but in other cases we do the rearrangement. So now the idea of the project is the following. In 2 dimensions, we observed 3 macroscopic phenomena. And what we want is we want to create a 1-dimensional model, because 1-dimensional models are easier, that would display the same properties. And the 3 properties are the following. Namely, we go from order to noise to order. The second macroscopic phenomenon is traveling wave phenomenon. And the third one is freezing at the boundary. So let's see if it works. What I'm going to do now, I want to show you some pictures and animations on Mathematica. So I'm going to stop sharing this screen and I will try to share something else. Okay. So let's see if you can, I hope that you can see this. Okay, so it's a simulation in 2 dimensions. The radius here is 200 balls. So from the center to the edge is about 200 balls. The initial configuration was that all velocities were 0, except 1. One in the middle, 1 velocity in the middle was non-zero. So think about this as an explosion. So you see that the energy is spreading from the center to the to the boundary, to the edge. And this is the configuration in the middle of the evolution. And it looks like it's a wave in the sense that, in the obvious sense, right? The energy sort of spreads radially and forms some kind of annulus of energy. So next, let me try to run animation. Let's see if you can see this. So the way you should interpret this is the following. On the left, you have the center of the disk, and on the right, you have the edge. So this wave of energy is traveling from the center to the edge, to the boundary. So this is what I meant by the traveling wave. Now, the next picture. So this picture was recorded, this is a recording of the middle of a evolution, somewhere in the middle of time. So I'm not going to any details. Let me just say what the colors mean. You see on the outside, you see a lot of red. This is the frozen region. This is basically where the velocities are already in the terminal value, and you still have a lot of action in the middle, which is not obvious to me, because if I had to guess, it wouldn't be obvious to me why it would be in this order. Perhaps those velocities that are small in the center, they settle quickly, and those big velocities that are on the outside should take a lot of time to sort things out. And now somehow it works in this order, namely there's this freezing of velocities on the outside. Okay, so now comes the 1-dimensional simulation. So first of all, let me run it, and then I will make comments on this. Okay, So I hope that you can see this. So now I'm going to stop. Now we are in one dimension, and this is our toy model. In this toy model, in the first simulation, we start with the velocities ordered in the wrong order, so to say. Velocities on the left are positive, velocities on the right are negative, which means that all velocities want to go to the center. So they have to crash in the middle. And at the very end, they would be all ordered because, well, that's what the collisions do, right? The velocities should be ordered by the collisions. But let's see what happens in the middle. So there's one thing that I hope that you can see. The highest velocity is 0.04, but this is just the normalization, 0.04, and the lowest one is negative 0.04. Now let's go to the middle. You see, one may guess that the initial velocities are simply mixed up. No, they are not. Please note that you get velocities above 0.04, definitely above 0.05, and also smaller than negative 0.05. And also, the initial velocities were on a straight line, which means that you had the same number of velocities in every interval, right? Or how should I put it? The distribution was uniform. This is definitely not the case here because you have lots of small velocities over here because there's like little variance, little standard deviation, and fewer velocities that are big. So in this simulation, it is not true that the velocities simply get reordered. No, they get transformed, but in the end, they magically reappear to be the same. In the second simulation, I want to show you a traveling wave. So it was a different initial condition. And I guess it's pretty obvious that it's a traveling wave. But I just want to mention one thing. Visually, there's a huge tail on the left, right? But so the energy is leaking, but not much. This whole tail on the left contains only 5% of the energy. So this is not obvious. Just, I mean, I had to calculate it. Check the data. So it looks like it's very substantial, but it's actually very, very small. So most of the energy is in this traveling wave. And finally, I want to show you what happens when we start from white noise. So the initial condition was simply IID normal. And let me run the simulation. And the reason why I want to show you this, the main reason is because I want to show you the freezing effect. Please note that we have that freezing effect, right? The part of the space that is close to the endpoints is frozen first, and there's still noise in the middle. So these are, so the wave and the freezing at the endpoints are like in 2 dimensions. So well, I'm happy about that because it means that our model sort of reproduces those effects. Okay, so I'm going to go back to my PDF file presentation. Okay. So this is the model that we sort of guessed. This is our guess based on simulations. What we really observe is modulated white noise. So you take white noise and multiply it. By the way, sigma and mu are supposed to be deterministic functions. So W is random, but mu and standard deviation are deterministic. Why white noise? Well, first of all, there is numerical evidence, so I will not go into details, but analyze some of the data from simulations. But for mathematicians, I think that there is a much better argument than just numerical evidence. You see, in this model, energy is preserved. Okay, so this is a little bit tricky. Maybe we should talk about local energy, because energy is preserved even locally in the sense that, through the, see, even here, there isn't that much flow of energy through the boundaries. So it is not unreasonable to say that energy is preserved here. And here that standard deviation on the variance seem to be more or less constant. You see, since energy is preserved, it means that we preserve the sum of squares of velocities. And what we do is energy redistribution. This is some kind of random walk, and it's a random walk on the sphere. And then one can simply guess that this random walk will redistribute the probability distribution uniformly on the sphere. And if it does, well, that's what it is. The uniform distribution on a sphere is white noise. It's white noise in the sense of that the coordinates are IID normal for high dimensional sphere. So of course, this is a hand-waving justification, but I think it's it should be convincing for mathematicians. Why white noise? It's basically a random walk on a sphere, but except that everything here is modulated, so my argument could work only locally. Okay, so that's our white noise. And we have equations for momentum and energy. So I think some parts are easy to understand. You see, here's the Laplacian, and here's another Laplacian. And this simply comes from local redistribution of momentum and energy, because this is what I do. Well, that's built into the model. Now, as for the other terms, they come from calculations. So well, what I did is I took the discrete model and I calculated the evolution of the mean and the energy from the discrete model. And when we pass to the limit, then in continuous time and space, we get this these PDEs. Now, there's a parameter lambda here. You see, this parameter lambda comes from, I guess I could say discretization. You see, the role of the, or the effect of the first derivative and the second derivative is different. Well, think about the Taylor expansion, right? We have, I would say, delta or delta squared. So the way the first derivative acts upon the system and the way the second derivative acts upon the system is different. And in discrete simulations, when your interval, right, the line segment is a certain length. So in my simulations, it was typically 2000, 8000. Then that lambda should be of order 1000 or 10,000 to reflect the different influence of the first derivative and the second derivative on the evolution. So this is what this lambda is. Lambda is here introduced so that it can explain different behavior for simulations on different line segments. Now, so what one can do is one can take the first pair of equations, so and well, do some algebra and get the second pair. So please know that in the second pair of equations, we have equations for the partial derivatives for mu and sigma in time. Sigma is the standard deviation, so one could guess why standard deviation. Maybe we should have an equation for the variance, right? Mathematicians like variance. Why standard deviation? But you will see soon that actually it looks like having an equation for the standard deviation is better, makes more sense. Now, these are nasty equations, coupled PDEs, well, non-random, but first of all, they are nonlinear because we have the square of the derivative, and that's typically considered a nasty part of a nonlinear PDE. On the top of that, right, so we have the square of the derivative, and also we have 1 over sigma. That is also quite often considered to be nasty. So let's see what we can do about that. So, you know, I explained that we are looking for a toy model that actually has certain properties of the original model. So let's start with this transition from order to noise to order. You see, lambda is very large, and in this slide, I'm talking about noise. So what's going to happen? You see, on the left, mu sub x is negative. So what this means, then this will be a very large positive term. And therefore, sigma t, the derivative with respect to t, will be large and positive. And this explains the creation of noise. Noise goes from 0 to, well, to some non-trivial quantity. By the way, you may say, well, we have a problem at 0, right? Actually, no. If you simply think about a very simple equation, sigma t equal to 1 over sigma. This is a perfectly good equation. It's solved by the square root. The square root function. So it's not like a nasty singularity. And now on this side, mu sub x is greater than 0, right? So it means that the term that dominates, that lambda mu x, is now negative. So this suppresses the noise. And it suppresses the noise to the point that finally this positive term plays a role. But on the scale of this picture, this is invisible. So I can tell you, and you have to trust me, that actually on the right-hand side, this function is not deterministic. There's a lot of noise there, except that it's invisible because it's much, much smaller than the noise in the middle. So basically, this negative lambda mu x suppresses the noise to the point that it sort of balances the positive term. Okay, so this is the first of the macroscopic phenomena that I wanted to be somehow reproduced. Now, asymptotics. I have explained that lambda should be very, very large. Now, in the second equation, I divided the right-hand side by lambda, but you may ask, okay, so what happened on the left? I should have divided the left-hand side. You see, what I did on the left-hand side, I removed lambda because the only thing that it means is that you run your video at a different speed. And I'm not really interested in a very slow or a very fast video. So I want to run the video at the speed that I, a human being, can actually sort of meaningfully watch and interpret. So I removed the lambda on the left just to change the speed to the speed that we can find informative. But if you now look at the right-hand side, there are all those 1 over lambda terms. And when lambda is very large, they disappear. So I reinstated lambda. I removed all nonlinear terms and also Laplacian. And what we get is a pair of coupled linear equations. Well, it's the same term. And now, if you differentiate twice, once again, so the first equation with respect to x, the second one with respect to, yeah, I guess both equations with respect to x, and go with the algebra, you will see that actually mu and sigma have to satisfy the wave equation. And please note that this is important. This arrow goes only in one direction. The reason is that the first pair, the two functions are coupled, and in the second pair they are not. So the second system is not equivalent to the first one, because in the second system the two functions are independent, yeah, uncoupled. So it goes only one way. Well, but that's the wave. I told you that I believe that the system should display this wave behavior, and it does. Well, that's what it is. But actually, I don't know if these are all possible solutions, but these are like solutions that you can guess. You take an arbitrary function f, and just the wave equation moves it. But please note that for these solutions, sigma and mu have to be identical, or mu has to be the negative of sigma for this to work. Now, freezing. As for freezing, I don't have very much to say, except that I can reproduce it in examples. So, well, the examples are created by guessing. And well, as I said, you start with some function f, then you create sigma and mu, the solutions of the wave equation, or the coupled transport equations. And well, you do some calculations, and then you're trying to get the freezing effect. So what is the freezing effect? So there are two steps. The first step is here. You see, I look at a point x in space, and I say, I believe that the configuration will freeze at the x at some time. But what does it mean to freeze? To freeze means that there is no noise. So I write an equation, sigma of x tx is equal to 0. At the point x in space, there will be some time when the noise goes to 0. And at this time, the configuration will freeze at mu x tx. Why? Mu is the mean, sigma is the standard deviation. If the standard deviation is 0, then the random variable is equal to the mean. So this is the white noise becomes the white noise with 0 standard deviation, just a value, fixed value. And I call this value h of x. Well, h of x is the shape of the frozen part of the space. And well, on the right you see the formula. So as I say, this is a guess based on a number of hand waving steps. In particular, I neglected the nonlinear terms. Let's see if it works. So, well, you have to judge whether this is correct or not. I mean, correct is not the right word. Whether this is a good match. The red curve, or the polygonal curve, is the theoretical curve, and the blue curve is the result of a simulation. Well, obviously it's not perfect, but you have to remember this is actually a nonlinear equation, and I just simply ignore that nonlinear term, so it cannot be perfect. However, there's a little bit more to this. You see, so this is probably not clear from the formulas, that are here, but you have to believe me that the noise, according to those equations, this is just an explicit example. The noise goes to zero gradually. So the noise goes to zero gradually, starting from the boundary, going towards the center. So these two regions, according to the formulas, start freezing. But then at some point, this whole interval freezes at the same time. So there is a gradual freezing and then sort of instantaneous freezing. Okay, so let me try to share a different screen. Okay, so let me first run this simulation so that you can see the whole simulation. So in this simulation, well, randomness shows up and the left tail doesn't look like the right tail. Well, it's random. But let me show you a few things. So first of all, please note that the left tail, probably the left tail is like more informative, freezes. And then I will show you three crucial frames. This is the first one. This is the second one. And this is the third one. So let's go back. Please note that the noise between 500 and 1500 is more or less the same in the sense that the standard deviation is more or less constant. We go to the next frame. The noise is smaller, but once again, it is more or less constant between 500 and 1500. And then in the next frame, it is gone between 500 and 1500. So at this point, I was extremely proud of myself. And the reason why I was so proud of myself is because I felt like I'm a true scientist, a physicist. You see, in physics, what you do is you start with observations, experiments, you get some ideas, and you construct a theory. But then to confirm the theory, you have to make a prediction. You have to make a prediction of something that has not been observed before. And in this case, my example showed the instantaneous freezing on a large part of the interval. And that was my personal prediction, because that was a phenomenon that I had not observed before, or perhaps I haven't noticed it before. So I was so proud of myself that my calculations predicted the event that was confirmed by the simulations. If I can take a minute or two, is that okay?
Sure.
Okay, so I will try to share something else. Okay, give me a second. Okay, so what you see here is this is the mu, these are the velocities that are ordered in the wrong way. Positive on the left, negative on the right. And what you see that green stuff, the green line is the noise. No noise at the very beginning. So this is not a random simulation. This is a numerical solution to the PDEs. Actually, I believe, because this is Jeremy, this is what Jeremy did, and this is the simulation. Actually, I think using the form with nonlinear terms, but those nonlinear terms don't matter very much. And this particular case can be actually confirmed with calculations. Well, confirmed, agrees with an explicit algebraic example. So you recall that we started with a straight line that was decreasing, and we end up with a straight line that is increasing. Okay, so I guess I will stop sharing at this point, and if there are questions about anything, then I would go to one of the screens that I shared, but otherwise, well, thank you very much for your attention.
Thank you very much for the interesting talk. We have plenty of time to ask questions. Are there questions and comments?
So, Chris, you say you didn't see the simultaneous freeze in the two-dimensional simulations. Do you see it now?
I do not recall any simulations. Perhaps I started with the wrong initial conditions. You see, because in one dimension, I was more adventurous in the sense because the one-dimensional simulations are easier to run or shorter. And in two dimensions, I even didn't know that such a thing would exist. So I wasn't looking. So perhaps now I will try to find initial conditions that would show that.
Because that would be a nice discovery, wouldn't it?
Exactly. But I will have to think about this, how to create the initial conditions.
Thank you very much. Very interesting talk. And I have a question. Somebody probably immediately will start thinking about infinite billiards. So it seems that stochastic differential equations, they are the same, and the difference only in initial conditions, where you have like localized conditions and when you have initial conditions over all space. So do you know anything about conditions where you have not localized initial conditions or behavior?
Okay, so to be honest, I don't have much to say about that. I thought a little bit about some special cases. You see, I'm interested, for example, in the stability. I didn't talk about this. I presented the terminal configurations as fixed lines. They're not. They will keep evolving forever. And in that context, it is natural to ask what happens in the infinite configuration. And that one that is interesting to me, of interest to me, is when you have a monotone increasing line with noise, because that noise will affect the configuration. And it appears to be stable, but this is the only case when I thought about an infinite configuration. But you're right. I mean, but one should think about this. But I haven't thought about this yet.
Okay, thank you.
Hi, Krzysztof. Thank you for the very nice talk. So in the one-dimensional case, so you're considering the situation where the balls are lined up in a line from the left to the right, right? So what if we close up the line, for example, by allowing the most left ball to collide with the most right ball? Another way to look at it is thinking
it's
of
a torus. Yeah, a torus. We're talking about one-dimensional torus, but one could think about two-dimensional torus, for example. Yes, so I thought about the torus. You see, the thing with the torus in one dimension and in any dimensions is that there will be no terminal configuration, because some balls will collide. So one could ask about not the terminal configuration, but about the stationary distribution, and it's a very natural guess that the stationary distribution should be white noise. In other words, IID. Normal random variables. This is not the case for a finite torus, because for the finite torus, one can easily show that it cannot be exactly, IID normals. But one can guess that this goes back to the previous question. This could happen in an infinite system. IID. That's a very natural guess. So actually, I gave this problem to my student, but well, he failed, and I don't want to say that it's his fault. Maybe it's too hard to prove, but so far, this is just a conjecture. I don't know what to do about the finite torus. For the finite torus, I guess the guess is that the distribution is close to IID normal, the stationary one, but I'm not sure how to. The only way I can think about this is to prove some kind of asymptotic theorem. That would be a meaningful theorem. Asymptotically, it is IID normal.
Thank you very much.
Okay, any other questions?
May I ask one question more?
Please.
You somehow transform your problem to problem-solving stochastic differential equations or system of stochastic differential equations. And your particular type of collision somehow corresponds to one type of this equation. So probably you can introduce some other classes of equations and look at correspondence between coefficients and collisions. So I understand that equation is not very easy or very complex, but at least maybe from some general point of view on stochastic differential equations, can you just, can it contribute to characterize some properties of solutions?
Okay, so so this somehow goes back to that part of the talk that I did not present to you. You see, I used to work on deterministic problems concerning collisions of billiard balls, like estimates of the number. And I worked only exclusively with the case when all balls have the same mass and same radius. The reason is that once you drop this assumption, things become scary. Much more difficult. At least that's how I see things. So you're right that by changing the model, and you're right that, for example, in a number of publications, other authors considered actually changing the laws of physics, for example, to conserve only momentum or only energy, or change, the rules. So there is literature already on different collisions, but honestly, I find it scary. So I would rather try to say more about this model and perhaps prove some theorems before I go to other models.
Yes, thank you.
Okay. Any more questions?
Can I ask a very quick question?
Please.
Like rather peripheral. The distribution, uniform distribution on a large ball, I think this is the characterization of Maxwell for the normal distribution, isn't it? And
Okay, so well, first of all, the distribution on a very, very large ball is only approximately
yes.
IID normal.
Yeah.
But the characterization of the normal distribution that I know is that if you have, let's see, so in 3 space, so you don't, this is not asymptotic. If you have vectors that are independent and the distribution is invariant under all, so this is not really on the ball. This is 3 vectors that are independent in free space, and the joint distribution is invariant under all, action of the group, right? Yeah, all rotations.
Okay.
So I thought that this was Maxwell, but maybe I'm wrong.
Well, I thought that Maxwell means because he had like a room with n velocities, the sum of vi squared equals constant for I equals 1 to n, where n is 10 to the 20.
Yeah.
That means uniform distribution on a
sphere,
ball of
on a
radius
sphere.
n, or square root of n actually, and that by central limit theorem you can show that it is Gaussian. So my question was rather historical. I think that this is one of the first characterizations of the Gaussian, but I may be wrong.
Yeah, might be.
Because
since you asked about characterization, so let me do a plugin, but it's not for myself, but for a friend.
Okay.
Włodek Bryc, B-R-Y-C, has a book. I think it's called On Normal Distribution, on Gaussian Distribution, something like this. And he has lots of, like 1 million characterizations. And I'm pretty sure that he has also historical remarks.
Okay, thanks.
Okay, it's time for us to wrap up. Okay, thank you very much for the very interesting talk. Let's thank Krzysztof, please.
Well, thank you very much.
Thank you.
Thanks, Chris.
Thank you.